We're going to start our unit on organic chemistry by learning how to name compounds. And honestly, a lot of organic chemistry at this level is naming organic compounds. So we're going to spend a lot of time naming things. We'll talk a little bit about reactions, but that's as far as we're going to get this year. So methane, ethane, propane, butane, these are all examples of organic compounds. And organic compounds are just carbon-containing compounds, carbon-based compounds. So methane, for example, is CH4. And so here's our chemical formula. That's our chemical formula. We can also draw a structural formula, which looks like this. And we're going to talk about several different ways to represent these as we go through these. So here's ethane, C2H6. So that's 2 carbons. And each carbon needs 4 bonds to it. So that's how I'm knowing how many hydrogens to fill in, right? Because carbon is one of the very few elements that has to follow the octet rule. So it's usually going to have 4 bonds to it. All right, propane. Well, propane, hopefully you're seeing the pattern here that I'm doing 1 carbon, 1 central carbon, then 2 central carbons, then 3 central carbons. Okay, so here's propane. And when I do that, I end up with C3H8. And then butane. Why don't you pause and see if you can do butane? So butane is going to be 4 carbon, a 4 carbon chain with hydrogens all around it. And that'll be C4H10. So naming alkanes is actually like really easy, okay? So alkanes are what we call saturated hydrocarbons. And saturated means like full of something like that, okay? These are saturated or full of hydrogen. And we'll talk more about like saturated hydrocarbons versus other types of hydrocarbons. But alkanes don't have any double bonds or triple bonds. They're all single bonds. Okay? And for alkanes, they have a general formula of some number of carbons, and then for the hydrogens, we take twice the number of carbons and then add 2. Okay? And this is really important because you need to be able to easily identify what type of compound you're looking at from the formula. Okay. So here are 3 more examples. So why don't you see if you can pause the video, see if you can either name them or give the structural formula and then also the chemical formula. So this first one has 1, 2, 3, 4, 5, 6, 7, 8. 8 carbons. So if I go back up to my list, methyl, ethyl, propyl, butyl, pentyl, hexyl, hepta, octyl. So this is going to be octane. pentane is going to have, oh, sorry, this is also C8H18, and then pentane is going to have 5 carbons, and I'll fill in hydrogen all over the. Okay, and that will be C5H12. And this is 1, 2, 3, 4, 5, 6. So this is hexane. And C6H14. So hopefully you were able to get all those pretty easily. Yeah, let's continue on. So we can also represent pentane. So again, here's pentane, C5H12. We can represent that as a what's called a condensed structural formula. So on this first carbon, there are 3 hydrogens attached. So I write CH3. And then on the next carbon, there are 2 hydrogens attached. So that's CH2. Now, the next several are CH2s. 1, 2, 3 are CH2s. And then we have another CH3. So condensed structural formula is another helpful way to represent the attachment of atoms in a molecule. The other way that we can do this is a line structure. And the line structure for pentane looks like this. So this is the line structure for pentane. So if we look, okay, like right here, in the line structures, a bond is represented by a line. Okay? The carbons are at the end of lines. Okay? So this blue one that I've circled, that is equivalent to a CH3. And then here, as we go from the CH3 to the next carbon, so here's a line, so there's a bond. That means that this corner right here is the end of this line. And that corner then represents a carbon. And that carbon has 1, 2 carbons attached to it, which means that this is a CH2. Okay, so this one is a CH2. This one is also a CH2, that one is also a CH2, and then we get to the end, that one's a CH3. So the line structures are really, really helpful, right? So if I go back and I look at some of these other things, well, methane doesn't really have a line structure. It's just kind of methane. But ethane, the line structure for ethane would just be a single line. The line structure for propane would look like that. See how much faster that is to draw? You know, we can go up to something like octane, right? 1, 2, 3, 4, 5, 6, 7, 8. 8. See how fast that is? Okay. So we have a lot of different ways of representing a compound, right? I could use the word, like butane. Okay. I could do a structural formula. So that would be 4 carbons attached. I can do a condensed structure. I could do a line. Okay. I could also, if I was being super crazy, I could do a Vesper. And all of these carbons have just four bonds attached to them. So they're all tetrahedral. So this Vesper geometry is the best one we have, right? This is the most realistic. It's also the biggest pain to write and the one that we use probably least. Okay, so these are all ways that we can represent butane. So you just need to you need to um, you just need to be aware of that. All right. So I want you to take a pause. Draw the condensed and line structure for C4H10. Give it a try. So condensed structure, and if you're paying attention, we just did this. This is butane again. We could do that, right? But what about this? Does that also work? Let's see. So here's our C4H10. Here's 4 carbons, and then 3, 6, 9, 10 hydrogens. So this structure does work for C4H10. Okay, it's no longer butane. Okay, it's something else. It's actually a propane. But these are the same formula, but different structures. And really what I mean by that is different attachments of atoms. Okay, these are what are called isomers. Okay, these are isomers. And these two are examples of structural isomers. Next time we're going to talk about a different kind of isomers, but this is different groupings branching from the main carbon chain. Okay, so again, these two compounds, both C4H10. Okay, they're not both butane, they're both C4H10. They are isomers of each other. They are also structural isomers. All structural isomers are isomers, not all isomers are structural isomers, that kind of thing. Okay? So, I want you to give this a shot. This is a little tricky. I want you to give this a shot. I want you to draw all 5 isomers of C6H14. All right, so there are kind of 2 ways that I think you can do these, finding these isomers pretty easily. And that is either as a condensed structural or a line. And I'll show both, okay? So what I do is I start with the number of carbons in the chain. So I have a 6 carbon chain, and I know that the exterior carbons are going to have CH3s and the interior ones are going to have CH2s. So there's 1, 2, 3, 4, 5, 6. Okay, so there's a 6-carbon chain. So there's my first isomer, and I can draw that again as a line structure. 6. Okay, now the next thing that I'm going to do is I'm going to make the carbon chain one shorter. So now I'm going to do 5. Okay, so now we're 5 carbon chains long, which means that I have one more carbon left. Oh, and when doing this, it's best to just put the carbons in first. Okay, sorry. Just put the carbons in first. Now, I can't put that next carbon off of the end because then that's the same structure as this one. Okay, so I can't put it there. But I could put it here, and that's no longer the same molecule. They're not all in the same thing, which will make sense once we put our hydrogens in. So all exterior hydrogens are CH3s. These ones are CH2s. And then this one, this carbon here, has 1 carbon, 2 carbon, 3 carbons attached. So it only needs one more attachment, so it gets a hydrogen. Okay? So again, same thing if we're doing the line structure. I'm just going to take my line structure, I'm going to make it one shorter, and then I'm going to try putting my that extra carbon somewhere else. Okay, now I could take this carbon and I could move it over to here. Okay, this is now a different compound. Okay, instead of this carbon branching off the 2nd carbon from the right, it's now branching off the 3rd carbon from the right. This is a different structure. There's the line, it's a different structure. But what about this one? What if I try to do then okay, what do we think about that one? Well, hopefully we see that this one is actually exactly the same as that one. I've just taken them and I've flipped them. So instead of coming off the 2nd one from the right, it comes off the 2nd one from the left. Okay, so this is actually not one of the isomers that we can use. Okay, so I've kind of exhausted all my options for putting this carbon in with a 5-carbon chain. So the next thing that I can do is I can go to a 4-carbon chain. And we know it can't go on the ends because that would create something else. Now I've got 2 carbons to play with. I could either do the 2 carbons separately, so I could put a carbon here and off the same carbon and a carbon there. So we do this one. That one works. We could also put them off of different central carbons. Okay, so that's 2 other isomers. So we've got 1, 2, 3, 4, 5. Now, just to kind of prove something, I want to say the other thing that I could do is I could take those 2 carbons and put them into one thing where I go like this. Okay, so this is CH3, CH2, that's CH, CH2, CH3. Now, this one's going to be a little harder to see, but this is also, this one is that compound, right? It's got 1, 2, 3, 4, 5 carbons in the longest line that we can count. This one has 1, 2, 3, 4, 5 carbons in the longest one that we can find. We call that the parent hydrocarbon or the parent carbon, or the backbone. So these two are actually the same. So I can't actually do that, which means we're done. Okay, I can't go down to a 3-chain for much the same reason. Okay, so if I ask you to draw isomers, this is kind of what you got to do. You just got to exhaust all the options until you get down to a base geometry, or until things stop working. All right, so all these ones up here, like this one, and this one, and this one, and this one, are different than the green one. Okay, the green one, all the carbons are in the backbone, are in one chain. All the other ones, there's a carbon coming off. These are called branched alkanes. And branched alkanes have a whole nomenclature thing that you have to know. So why don't you pause it, write all these rules down so that you remember them, and then we'll go through some examples. Okay, so the first thing that we got to do is find the parent hydrocarbon. It's often the longest carbon backbone. Most of the time, for us, it's going to be the longest carbon backbone. If you can count two different ways and the carbon backbone is the same length, use the one with the most branches. And there's a little thing here. If there is a branch that you don't know the name of, redo the backbone to include the greatest number of branches, right? So for example, if I start numbering this one this way, oh, that's going to mess me up later. Okay, now I don't know that the name of that is going to be a little bit tricky. Okay, but I could also do that, or alternatively, I could go, instead of naming to that one, I could branch off to that one. They're the same. Okay, so we can't do the green. Green, bad. No green. The blue is interesting because we could either do that or we could go the other way, which I'm going to do in black. 1, 2, 3, 4, 5, 6, 7, 8. Either way, we found our longest backbone. Okay, that's our parent hydrocarbon. So we know that this is going to be an octane. Okay, so this is going to be an octane. Now, we got to go through, and I want to do I'm going to actually kind of do number 4, or actually, sorry, we'll do number 2. Okay? Add names of alkyl groups in alphabetical order before the parent name. So either way, I have this branch, this branch. Here, I'm going to okay. I have this branch, this 2-carbon branch here, and this branch here. So these branches are just carbons with hydrogens attached. So we call these alkyl groups. Okay, alkyl groups are just carbon, hydrogen with single bonds. Okay, and we name alkyl groups exactly like we did these. Okay, but instead of alkanes, instead of like methane, it would be alkyl, which is methyl. So we could have alkyl groups that are like methyl, ethyl, propyl, and so on and so forth. Okay? So I've got 3 methyl groups. So I've got methyls, and I also have the CH2CH3 group. That is an ethyl group. Okay, so we've added names for the alkyl groups in alphabetical order. Okay, so the ethyl is going to come first, and then the methyl. Then we add Greek prefixes to the alkyl groups to account for quantity. Okay, so this methyl group, so the Greek prefixes are like mono, di, tri, tetra. They're on that the polyatomic ion sheet. Okay, so this is going to be trimethyl, and there's nothing for the ethyl. You don't do like monoethyl, so it's just ethyl and then trimethyl. Then we need to number the carbon atoms in the parent hydrocarbon. These numbers should give the lowest numbers possible. Okay, so I already kind of went through. So what this means is I'm just going to be comparing the blues now. We already determined that the green wasn't a good way to do this. Okay, so if I name the blues, if I name with the blues, this methyl is 4, this one's 5, and this one's 7, and this ethyl group is 6. So this would be 4, 5, 7, trimethyl, 6, ethyl. Okay? And with the black, this one is 2, this one is 4, this one is 5, and this one's 3. So we can see that the numbering of this one, the alkyl groups, are going to be numbered, have lower numbers. Okay? If there's a tie, like let's say that we had, a CH3, a CH, let's see, how could I do this? CH2, CH2. So I'm going to need to. So I could do a methyl group here, and an ethyl group here. And no matter which way I number in the backbone, if I go 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6, okay, they both have the same numbering. Okay, in that case, then you'd go, if there's a tie, it goes to the alkyl group that comes first alphabetically. Okay, so let's go back to our main example here. So we're going to use this black one. So insert position numbers. And the way that position numbers get inserted is just numbers in front of the, like the trimethyls. So this is 2, 4, 5. And then you put a little hyphen, 2, 4, 5, hyphen, trimethyl. And yes, trimethyl is one word. I know I messed that up. And then the ethyl group on this one would be 3-ethyl. So the name, the full name for this is 3-ethyl, because the ethyl group is going to come first alphabetically. Then 2, 4, 5 trimethyl octane. Okay, you can put a dash between the trimethyl and the octane if you want to. You don't you don't need it, and most places won't put it there. It's not like super wrong if it is there. I'll accept it either way, but you don't need it. So this is 3-ethyl 2,4,5 trimethyl octane. Okay. Let's go on to the next one. All right. Why don't you pause here and see if you can get this? Okay. See if you can get this. So the longest chain here, 1, 2, 3, 4, 5, 6, 7. That's longer than, say, going 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. That's the longest straight chain of carbons. Okay, I can number it going one of two ways. Okay. And the green way, my numbers are 3 and 4. The blue ways, my number is 4 and 5, so we want to go with the blue way. Okay. Oh, sorry. No, we want to go with the green way, not the blue way. Okay. So then the ethyl is going to get named first. So that's 4-ethyl. Okay. Sometimes I'll write them out to the side. So like 4-ethyl and then a 3-methyl. So that's 4-ethyl, 3-methyl heptane. All right, give this one a try. Condensed structural formula for 3,3,4 triethyl 4-methyl So the way that I'm going to approach this one is I'm going to do my hydrocarbons first. And you'll notice that when I do these, I'm leaving plenty of room, like in between here and the dash, so that I can fit any hydrogens in that I need. So this is a hexane, so I need 6 carbons in my backbone. All right. And then I'll start putting the things in. So I'll just number this way, 1, 2, 3, 4, 5, 6. And I'm going to do a 3. At 3, I'm going to do an ethyl group. So that's 2 carbons. And then another ethyl group on the other, coming off the other side. And then another ethyl group coming off the other side, coming off of 4. And then a methyl group there. And now I can go back through and fill in all the other hydrogens in the base, the parent hydrocarbon. Okay, last but not least, give this one a try. So here, this is a pentane, so it's a 5-carbon backbone. Okay, and then I'm just going to number from the side, so 1, 2, 3, 4, 5. So 3-ethyl, and then 2,2-dimethyl. There's a methyl group, there's a methyl group. So now I can fill in the backbone. This carbon has 3 carbons attached. Okay, so there's my thing. You don't necessarily need to include these numbers, right? And in fact, if we go back through and clean it up a little bit, it looks a little bit nicer. Okay, let's give this one a try. I'm going to do something a little different. try naming that. So my longest my parent hydrocarbon is going to start here. So 1, 2, 3, 4, 5, and then we can either go 6, 7, or we could go down here 6, 7. So it doesn't really matter. So just for funs, I'm going to go the other way. Okay, and then for the numbering, I can do blue, or I could do green. Okay, and either way, my branches are going to be at positions 3 and 5. So this is tie. So this is tie goes to the numerical group. Okay, this side chain is an ethyl, and this side chain is a methyl. So she's okay. So tie's going to go to alphabetical winner. So that means that I'm going to end up using the green numbering because that puts this ethyl group at position 3 rather than position 5. Okay, so this is going to be 3 ethyl, 5 methyl, and then it's a heptane. So 3 ethyl, 5 methyl, heptane. Okay, so we've done plain alkanes. We've done branched alkanes. Now the other thing that can happen is that these carbon chains can form rings like this one. These are called cycloalkanes. So cyclo meaning rings, kind of like a bicycle tire, a cycle. Are alkanes where the carbon backbone is arranged in a ring. Cycloalkanes have a general structural formula of C to the N, H to the 2N. So there's no 2N plus 2. It's actually got 2 fewer hydrogens than an alkane or a branched alkane. Okay, but naming these is pretty easy. Just add the cyclo prefix to the name. And we number to give substituents the lowest number possible, and tie goes to alphabetical. So if you're going to have your substituents, your side groups, have the lowest number possible, you're going to start naming or start numbering on one of the substituents. So I could either do the blue, 1, 2, 3, 4, 5, or I could do the green, 1, 2, 3, 4, 5. And if I do oh, I just realized I messed up the blue. The blue doesn't make any sense. The blue would go this way. 1, 2, 3, 4, 5. Okay? So either way, my substituents are going to be numbered 1 or 2. So tie goes to alphabetical. This is once again an ethyl and a methyl. Okay, so we're going to end up using the green. So this is 1 ethyl, 2 methyl, cyclo, there's our addition, cyclopentane. Okay, you see how that's done? And that's it for today. So we did naming alkanes, we did naming